In this lecture, we continue our discussion on canonical correlation analysis. Now, in the last lecture, at the end, what we had looked at was the following concept, that we were looking at the correlation coefficient between the canonical variables and the original variables. We had come up to the following point, that we had noted that if we denote by u vector the p-dimensional vector containing the canonical variables, the first component of the canonical variable pairs, and x to be the vector of original random variables, then what we are having is that the covariance between u vector and x vector is covariance between ax and x vector, which is equal to a times sigma 1 1, which is given by this, and similarly the covariance between v vector and y vector can be given by this, and other combinations like the covariance between u and y or v and x can be similarly be obtained. Now, at this particular point, what we note is that this variance of, we have not yet got to the correlation coefficient between the two vectors. We have at the moment looked at the covariance structure. We note that this variance of ui, because they are canonical variables, that's equal to 1. So, this would imply that the correlation between ui and say xk, ith component of this u vector and kth component of x vector, that is going to be given by the covariance between ui and xk, which is going to be the ikth element of this particular matrix, because this is the covariance matrix of u and x, and what we are talking about is between the ith component of u and the kth component of x. Now, this would be divided by the standard deviation of the respective components. So, this will be 1 times, let us write this as sigma kk to the power half, wherein this variance of xk we are denoting by sigma kk. So, the standard deviation is this quantity. Now, if we look at this term here, this is nothing but the covariance between ui and sigma k to the power minus half times xk, because if we look at absorbing this particular constant as in here sigma kk to the power half into this variable here, we can write this statement as covariance between ui and sigma kk to the power minus half times xk. So, correlation between these two variables is just equal to this. So, using this particular fact, what we can say is the correlation matrix between u vector and x vector, which is the correlation matrix between u vector and the x vector, would be the same as the covariance matrix of u vector that multiplied by v11 to the power minus half times x, where v11 is basically what we have defined earlier, this diagonal matrix containing the diagonal elements of sigma 1 1, that is, this is a diagonal matrix containing sigma 1 1, sigma 2 2, sigma kk and sigma pp as the diagonal entries of that particular matrix. So, if we look at this v11 to the power minus half, it is basically what is serving the purpose of sigma kk to the power minus half for these two univariate random variables, and hence this one can be easily be computed. Now, by the previous calculations, what we had shown was that u we had denoted by a times a is that p by p matrix times the x vector, where a is e1 prime, e2 prime, ep prime sigma 1 1 to the power minus half. So, we will use that particular fact and write this u as ax. So, this is the covariance matrix of ax and v11 to the power minus half times x, and thus this is nothing but equal to a times the covariance matrix of x, which is sigma 1 1 times v11 to the power minus half. So, this is the final form as such of the correlation matrix between the canonical variables and x's, where ui's are the canonical variables using the linear combination of the elements of x's only. Now, if you look at this form, one can alternately write it in terms of the correlation matrix. In what way? we can write this expression here as A times V11 to the power plus half into V11 to the power minus half times sigma 11 into V11 to the power minus half. Now note that this particular matrix is nothing but the correlation matrix of the x random vector. So this is V11 to the power half times this rho 11. It's an alternate equivalent form of this correlation matrix between u and x, right. So in a similar way, we can look at, actually we can compute the correlations between the other pairs. So we derived this one explicitly. So if one is looking at similarly correlation between u and y, note that here we had written this v vector as b times y and u as a times x. So when we are looking at this correlation matrix between u and y, the other vector, so this would be similar to this one, the covariance matrix between u, and by in y what we are going to do is to take V22 to the power minus half times y. So this correlation matrix will be equal to this covariance matrix, wherein as before we take this V22 to be the matrix with diagonal entries as the diagonal elements of this sigma 22 matrix, that is, this is sigma 11 corresponding to the y variable, sigma 22 to the power not to the power sigma 22y. So this is the 22th element in this sigma 22 matrix, which denotes the variance of y2 in this y vector, and this is sigma q q because y is q dimensional, and we will have this as this, right. And this can be easily be computed because this is the covariance. In place of u, once again what we write is ax, and this is V22 to the power minus half times y vector. So this covariance matrix is going to be A times the covariance matrix of x and y, so that is equal to sigma 1 2 times this V22 to the power minus half. Once again, if we want to write this, this is what? This is correlation matrix between u and y. So if we want to write this in terms of the correlation matrix, one can do so by introducing the appropriate diagonal matrix in order to write this row sigma 1 1 in terms of row 1 sigma 1 2 in terms of row 1 2. So in a similar way, what once again what we can write is covariance, this correlation between the other components, which is correlation between v and x. This would be the covariance between, now v is b times y, and this x we will write as V11 to the power minus half, this is the covariance now, times this x, and thus this is going to be b times covariance between y and x, that would be sigma 21 times V11 to the power minus half, and the last component that what one can write is correlation matrix between v and y that we have not looked at. So this is going to be the covariance matrix between v and y would be standardized to have unit variance. So this we require V22 to the power minus half times y, and thus this is going to be same as covariance between by and V22 to the power minus half times y. This is going to be equal to b times sigma 22 into V22 to the power minus half. So we have computed all the four possible correlations that may exist. So one is this u and x, which is the final expression of that is given by this. So this is one. This is the second expression where we are looking at u and y. This is the third expression, and this is the fourth expression. So this 1, 2, 3 and 4 gives all the correlation matrices between the original and the derived or the canonical variables, right. Now we put it as a note here, an important thing. Suppose we are using standardized variables, that is, instead of the covariance matrix we are going to work with correlation matrix. Then if we are looking at the correlation matrix and then the canonical variables derived from the correlation matrix, if we compute the correlation matrices of the canonical variables derived from such a matrix and the original standardized variables, what would be the form of those correlation matrices and how does those compare with the original correlation matrices which we have just now obtained as 1, 2, 3 and 4, right. So, what we are now going to see, we had seen earlier was a thing that we had noted was that if we are looking at the covariance matrix between x and y given by sigma 1 1, sigma 1 2, sigma 2 1 and sigma 2 2, then if we are deriving the canonical correlation coefficients from that matrix, the canonical correlation coefficients from that matrix are going to be same as that of the canonical correlation coefficients derived from the row matrix. Now, row matrix is of course the covariance matrix between the standardized variables, right. Now, we are going to see the similar result here. Now, suppose we use standardized variables here, standardized variables, say the standardized variables I denote by Z1, which is the standardized form of x vector. So, how we are going to standardize that? Suppose we have mu x as the mean vector of x, and then this has to be multiplied by v11 to the power minus half, and the second component vector, which is y, is standardized as y minus mu y times v22 to the power minus half. So, these two are the standardized variables. Now, the covariance matrix of this standardized set here Z1 and Z2, this is going to be the covariance matrix of Z1 here. What is the covariance matrix of this element here? It is just equal to rho 1 1. The covariance matrix of this element here would just be rho 2 2, which is the correlation matrix corresponding to the y vector, and this is going to be the cross rho 1 2, which is the covariance matrix between Z1 and Z2, and similarly this is rho 2 1, which is the transpose of rho 1 2. Now, if we look at the canonical correlation coefficients to be derived from this is the row matrix, canonical correlation coefficients derived from row matrix or the original sigma matrix are same. The canonical variables are given by the following. So, canonical variables derived from row matrix are given by the following. Let us denote that by u zk to denote that this is the kth canonical variable computed using the standardized variables which we have denoted by z. So, this is given by ek prime, then sigma 1 1 to the power minus half times this v11 to the power plus half times z1. So, this is what is the form of the canonical variables derived from the row matrix. The canonical correlation coefficients remain the same as we have said, and similarly the v component, if we are denoting that by vzk, the kth canonical variable which is going to be derived from z2, this is going to be given by fk prime sigma 2 2 to the power minus half, then this is v22 to the power plus half times this is z1 vector and this is z2 vector, we have denoted by upper 1 entries. So, I will just stick to that. This is z1 and this is z2. So, these are the two canonical variables derived from the row matrix. If we write this u z vector containing all these entries, so this is going to be u z1, u z2, u z p, because the starting order there was p dimensional. So, this is going to be given by, in a similar way to what we had done for the canonical variables derived from the sigma matrix, we will write this as E1 prime, E2 prime, EP prime times this sigma 1 1 to the power minus half times V11 to the power half Z1. So, we just denote this term by the quantity which we are saying that it is just equal to a Z matrix, where a Z matrix is this entire matrix up to this times this Z1 vector, and similarly we will denote this Vz vector to contain these q canonical variables. This is Vz1, Vz2 up to Vzq. So, this vector is going to be given by this f1 prime, f2 prime, fq prime times sigma 22 to the power minus half V22 to the power plus half times this Z2 vector, right. So, we will denote once again starting from this matrix up to this matrix here by a matrix which we denote by Bz. So, this Bz matrix times this Z2 vector. So, this is what we are going to get if we are looking at the standardized variables. Now, similar to what we were calculating when we were looking at the canonical variables computed from the covariance matrix, this row u, x and things like that, the 4 expressions 1, 2, 3 and 4, we can compute the similar things when we are looking at the canonical variables derived from the row matrix. What we are going to get is the following, that this row uz, this is the vector of the canonical variables derived from the row matrix, and z1 vector which is the vector of standardized variables. This is going to be, now when we are looking at the standardized variables, these are going to have the matrix, the covariance matrix, which is going to have identity elements in its diagonals. So, we can just write that this correlation between uz and z1 is just equal to the covariance between uz and z1. So, that is as simple as that, and what we have written for uz is az matrix times this z1 vector. So, this is the covariance between these two terms, and which is very simple. So, you just write that as az times the covariance matrix between z1 and z1. What is that? That is equal to rho 1 1. So, this is say 1 prime, this is a corresponding term to the correlation matrix between u, the vector of canonical variables, and the original variables. Now, the original variables are standardized, and hence we have got this as the form. Now, similarly, we can write that this correlation matrix between Vz and Z2, this is would be given by Bz times just rho 2 2. So, this is corresponding to that. This is V and this is Z2. We will also be able to write what is going to be the correlation matrix between uz and Z2. What would that be? uz is given by az times z1 and z2 is as it is. So, what we will have is az times the correlation and the covariance matrix between z1 and z2, which is going to be given by rho 1 2. And lastly, what we have not yet considered is the correlation matrix between Vz and Z1. What is that going to be equal to? That is the covariance between Vz, which we are denoting by Bz times Z2. So, this is just going to be Bz times the covariance matrix of Z2 and Z1, that is equal to rho 2 1. So, these are actually the corresponding forms of 1, 2, 3 and 4 in appropriate orders when we are looking at the canonical variables which are computed from the row matrix. Now, an interesting thing is to see whether there is any change in this correlation matrices. Realize that when we have denoted this Az matrix by the following matrix, which is E1 prime, E2 prime, EP prime, that times sigma 1 1 to the power minus half times this V11 to the power plus half. So, this is that Az matrix, and what we have earlier obtained was that rho between u vector and x vector was equal to A times V11 to the power half times this, what we had derived earlier in this one expression here was that this is the correlation between u and x. We had denoted that by a times sigma 1, we had actually derived it to be equal to a times sigma 1 1 times v 1 1 to the power minus half, and we had seen that if we want to write it in terms of the correlation matrix, then this correlation matrix between u vector and the x vector is given by a v 1 1 to the power plus half times rho 1 1. That is what we are using here. So, this is a times v 1 1 to the power half times this rho 1 1 matrix. Now, what we are going to do is we are going to write this A matrix. Now, what was A matrix? A matrix was E1 prime, E2 prime and EP prime, this times sigma 1 1 to the power minus half. This was what we had as the A matrix in the previous non-standardized variable setups, and what we have now is that multiplied by v 1 1 to the power plus half times this rho 1 1 matrix. Now, what is this in terms of AZ matrix? This is E1 prime, E2 prime, EP prime multiplied by sigma 1 1. So, this basically is this matrix itself. Starting from this up to this particular point, this is this AZ matrix itself. So, this is AZ times rho 1 1, which we have just now obtained to be the correlation matrix between u z vector, which is the vector of canonical variables obtained from the standardized variables, and the standardized variables. So, what is the observation? The observation is that the correlation matrix is unchanged under this particular change in the starting point, that instead of looking at the covariance matrix, we are now looking at the correlation matrix and doing the calculations, the derivation for the canonical variables straight away from the correlation matrix. Now, similar is the situation for the other expressions. We can also prove that the variance between the correlation matrix between v and y is what we have just now derived as bz times rho 2 2, which would just be equal to what this is vz times, this would be just equal to v times, sorry, this is vz and the z2 component. This is just going to be equal to the correlation matrix between v and the original set of variables, that is y. So, these observations implies that the correlations are not affected by standardization of the variable. So, whether we work with non-standardized variables, that is x1, x2, xp and y1, y2, yq, or we work with the corresponding standardized variables, we are going to have the same canonical correlation coefficients. We are also going to have these correlation matrices to remain unchanged. What is going to change little bit is the vector which is combining it, because anyway we are using the standardized variables. So, the canonical variables forms look a little bit changed, although it is not that much. So, what we are now going to see is to look at an example of the computational steps involved in this canonical correlation coefficient analysis. Computation of canonical variables and the corresponding correlation, starting from correlation or covariance matrix. Now, in this example we consider a z vector, which is a standardized variable, which is a vector of standardized variables, which is partitioned into two parts, z1 and z2. Now, this z1 and z2 are 2 by 1 standardized variables. So, we have this starting point, and this covariance matrix of z vector, the covariance matrix of z vector is the covariance matrix of Z1 component and Z2 component in that partition form. Now this is going to be given by, since these are standardized variables, in our earlier notations this we write as rho 1 1, rho 2 2, rho 1 2, and the transpose as rho 2 1. Now suppose these values are the following. We take the following numerical values of these 4 block matrices, 2 by 2 matrices each of them. So this suppose is given by 1 1, 0.4, 0.4. So this one, the second element, we take this numerical values as 0.5, a 0.6, 0.3 and a 0.4, and this block here 1 1, 0.2. Well, this is a symmetric matrix. However, this one is not a symmetric matrix, that is why it is required to write all the elements here. We can ignore to write this particular element here, because that is what is element of that symmetric matrix, and what we are going to have here is the transpose of this matrix here, right. So starting from this is the row matrix. Starting from this matrix, we will look at what theory we have learned and how to go stepwise in calculation of the canonical variables. So what we will first do is that, let me write that as step 1. Step 1, that is the first thing that we will be requiring, is to look at rho 1 1 to the power minus half. Why are we going to require that? Well, it will be evident very quickly. Now the numerical value of this rho 1 1 to the power minus half turns out in this particular example as 1.0681 minus 0.2229, and this entry is 1.0681. This is this element only. It is a symmetric matrix, and rho 2 2 inverse, that is also necessary. So from the 2 by 2 rho 2 2 matrix, we can easily find out what is rho 2 2 to the power minus 1. So this turns out to be 1.0417 minus 0.2083, and this also is 1.0417. So using these two, rho 1 1 to the power minus half and rho 2 2 to the power minus 1, and the forms of rho 1 2 and rho 2 1, we can calculate then this important matrix, which is rho 1 1 to the power half, rho 1 2, rho 2 2 to the power minus half, rho 2 1, rho 1 1 to the power minus half. So this is a trivial calculation with these two matrices and rho 1 1 and rho 1 2 and rho 2 1 as given earlier. This turns out to be, this is 2 by 2 matrix, which turns out to be 0.4371, 0.2178. This is 0.1096. This also is a symmetric matrix. So we have calculated up to this particular point. Now when we have this, then all the canonical correlation coefficients, the canonical variables, all the derived calculations like correlation between the original set of random variables and the canonical variables, all the things can actually be performed from this particular matrix. So first what we are going to look at is the canonical correlation coefficients. So step 2 is to look at this, and we obtain rho 1 star square, rho 2 star square. These are what? Eigenvalues of this matrix which we have computed, which is rho 1 1 to the power minus half, rho 1 2, rho 2 2 to the power minus 1, rho 2 1, rho 1 1 to the power minus half. Now it turns out that this rho 1 star square, the eigenvalue, the largest eigenvalue of this matrix here is 0.5458, and this rho 2 star square is small. This is equal to 0.0009. Now these two are the two eigenvalues of this crucial matrix. Now from here what we are going to get is the canonical correlation coefficients. This rho 1 star is the first canonical correlation coefficient, which is square root of this particular term, and the square root is approximately equal to 0.74, and this rho 2 star is a square root of this particular term, which is 0.03. So, the first canonical correlation coefficient is 0.74, the second canonical correlation coefficient is 0.03. Now, these are the canonical correlation coefficients. What are the canonical variables, which is important. Now, in order to calculate the canonical variables, we move on to this third step of this computational term. Now, what we need to find out is the orthonormalized eigenvector of this matrix corresponding to the eigenvalue, which is rho 1 star square, right. So, we need to calculate this E 1 corresponding to this rho 1 star square. It turns out that the orthonormalized eigenvector has this particular form. These numbers are 0.8947, 0.4466. So, this is the E 1 vector. Now, this would imply that the coefficient vector for U 1, the first canonical variable U 1, is going to be given by the following. What is that coefficient vector? That is rho 1 1 to the power minus half times E 1. Because we are working with the correlation matrix, we are considering this matrix as rho 1 1. If we had the starting point as the sigma matrix, the covariance matrix, we would have taken here as sigma 1 1. So, whatever is the starting correlation or covariance matrix, we will stick with that. Now, we will have this term coefficient vector to be given by this A 1, right, and this calculation of this one turns out that this A 1 vector is going to be given by 0.8561. So, these are the numerical values which are the elements of the first canonical variables coefficients, right. So, if this is A 1, then U 1, which is the first component of the first canonical variable derived from x's, this is going to be given by this E 1 prime rho 1 1 to the power minus half, this times x vector. Now, x is not there, we have a z 1 vector, because that is the standardized variables. So, what we are going to have this first canonical variable as 0.8561, that multiplied by the first element of this z 1 vector, this plus 0.2776 times the second component of the first vector, first standardized vector. So, this is as far as U 1 is concerned. Now, we move on to look at how to compute the V 2 vector, V 2, the canonical variable corresponding to the Z 2 variables. Now, in order to get to that, we would require the F 1 vector. Now, we realize that this F 1 vector, as we have seen in the theoretical lectures, that this F 1 is proportional to rho 2 2 to the power minus half times rho 2 1, that multiplied by rho 1 1 to the power minus half times E 1. So, we can explicitly compute this particular term here, but before computing that, we see that this particular term is just equal to A 1, right. So, and from here, of course, what we will be able to write is that this B 1, that vector, is going to be given by this rho 2 2 to the power minus half times this F 1 vector, whatever we are going to obtain. Now, this proportionality constant here is going to be obtained in the following way. Let us move on one more step, that is, from here we will write this F 1 as being proportional to rho 2 2 to the power minus half times rho 2 1 times this vector, what we have already obtained, and it turns out that the numerical values of this particular components of this particular vector with A 1 given by this rho 2 1 is a known thing, rho 2 2 inverse is a known thing. So, what we are going to have is to write the numerical values, which is 0.4026 after computations. So, this is 5443. So, this F 1 is going to be proportional to this. Now, how do we obtain the proportionality constant? Now, note that when we are going to obtain this B 1, now B 1 is the coefficient vector which is going to be multiplied B 1 prime times Z2 vector. Now that is going to lead us to V1. Now V1 is the canonical variable, so the variance of V1 is going to be unity, and that is where we are going to obtain the proportionality constant in this particular vector out here. Now since we will have this B1 vector defined as in here is such that variance of B1 prime times this Z2 vector, which is of course nothing but variance of V1, the canonical correlation variable, canonical variable. So this is going to be given by B1 prime, the covariance matrix of Z2, which is nothing but rho 22, this times B1 vector, that should be equal to 1. So when we have obtained this term here and the corresponding B can be obtained so as to satisfy such a condition that whatever the coefficient vector we are going to get by, because B1 is equal to this and F1 is proportional to this, F1 is proportional to rho 22 to the power minus half rho 21 times A1, we see that our B1, what we have written there, B1 is going to be proportional to rho 22 to the power minus half times this particular term here, right. So this is going to be, this B1 is proportional to rho 22 to the power minus 1 rho 21 times A1, right, where we have this term as, I am sorry, this is not this particular term, this is just this term out here. F1 is proportional to this, which is coming by looking at this term to be just equal to A1, and since B1 is equal to rho 22 to the power minus half times F1, we will have this B1 proportional to rho 22 inverse times this, and this vector, actually the final vector, turns out to be the previous vector that I had written earlier. So this is 0.4026 and the second entry is 0.5443 transpose. So this B1 turns out to be this. Now we will normalize this with B as equal to this previous vector 0.4026, 0.5433. We will have this B prime rho 22 B, this numerical value turns out that this is equal to 0.5460. So this would imply we now get the proportionality constant and the B1 vector as 1 upon root over of this particular norm, so that we will have 5460 under root here, and then this is 0.4026, 0.5443. So this B1 vector is the combining vector, and this B1 vector given by this, and hence V1, the first component there is B1 transpose times the Z2 vector, that is, this is going to be equal to 0.4026, that divided by 0.5460, that multiplied by the first component of the second set Z2, this plus 0.5443, that divided by under root of 0.5460, that multiplied by the second component of the Z2 component here. So we have this as the V1, and we have previously computed U1 as this. So U1 and V1 now comprise the first pair of the canonical variables with the canonical correlation coefficient as we have computed earlier. The canonical correlation coefficient corresponding to that first pair, that is the correlation between U1 and V1, is going to be 0.74. So once we have obtained the first pair of canonical variables U1 and V1, starting from this matrix, what we have computed, the crucial matrix, where is that? This rho 1 1 to the power minus half rho 1 2 rho 2 2 to the power inverse, wherein we had this as the largest eigenvalue and this as the smallest eigenvalue, because there are two eigenvalues only. Now the first canonical variables U1 and V1 were computed from the eigenvector straight away, as we have seen from E1, and all the computations basically rely on that. F1 is also derived from E1, in this way. So, if we further want to calculate the second pair of canonical variables, the u2 and v2, what we will have to do is to get back to this rho 1 star and rho 2 star and then compute E2, which is going to be the orthonormalized eigenvector corresponding to this rho 2 star of this matrix here, and then replacing E1 by E2, which should be the orthonormalized eigenvector corresponding to rho 1 rho 2 star square. We will do all these steps and we will get to U2 and V2. However, in this particular situation, we see that this rho 2 star is equal to 0.03, which is too small actually. So, if we are at all going to compute the second pair of canonical variables, that is u2 and v2, the correlation that we are going to get between u2 and v2 is going to be as small as 0.03, which is negligible, and hence we are not going to compute u2 and v2. We will see later on actually after this particular example that how these values of the canonical correlation coefficients can decide as to the order of approximation that one can obtain through these canonical variables, right. Now, as the last step, we will look at this correlation calculations. So, this will comprise the last step of this particular computational example. So, what we will look at is the correlation calculation or computation, correlation matrices between the original and the canonical variables. Now, what we have is for the first canonical variable pair actually, because we will look at in pairs, what we have is a z, it is a vector, the transpose of that vector is the coefficient vector 0.8561 is the numerical value, the second value was this term, and this B z transpose that is equal to 0.5448, 0.7366. So, these are the two combining vectors which is playing the role of A z and B z matrix as in the theoretical part. So, if we want to calculate the correlation between the first canonical variable u1 and the first set of original variables, this is, as we had seen in the theory, that this is given by A z times rho 1 1. So, for the given example, this with rho 1 1 value and this A z value, this is going to be a 1 by 2 vector, which is going to be comprising of these two elements, which is 0.97 and 0.62. What does this indicate? This is coming from the theory part, but what it indicates is important, that the first canonical variable u1 is highly correlated with the first component of this z1 vector, having a correlation of the order as close to 1 as possible 0.97, and the second component is of z1 is also fairly highly correlated with the first component of the first canonical variable pair. Similarly, one can obtain the other terms like correlation between V1 and the second component of that z vector, from where actually V1 is derived. So, this as per the theoretical notations, this was given by Bz times rho 2 2. This turns out to be that the coefficients of this vector is 0.69 and 0.85. So, if we look at the second component of the first canonical variable pair, which is V1, that is more closely associated to the second component of this Z2 vector than to the first component, with the two correlations reasonably high. And we can also look at the cross terms, that is U1 with Z2. This is was given by Az times, this is Az times rho 1 2. The numerical values of this is 0.51 and 0.63, and the other last one, which is V1 and Z1, This is going to be given by this Bz times rho 21. The numerical values of this is given by 0.71 and 0.46. So, this concludes all the calculations that we have done in the theory part to compute the canonical correlation coefficients, to compute the canonical variables 1 or 2, whatever is the desired number of pairs that one wants to calculate, and also for interpretation of those canonical variables one can look at this correlation coefficient calculations, and all of them can be done starting from that crucial matrix rho 1 1 to the power minus half, rho 1 2, rho 2 2 to the power minus 1, rho 2 1, rho 1 1 to the power minus half. Right. Now, we move on to the next concept, in which we are going to look at the following technique. This is a technique to check whether a fewer than the original variable dimension, whether a fewer number of canonical variables is enough. So, this is what the concept is, and we are going to now look at how to check. What we are actually trying to convey by this particular technique or achieve by this particular technique is the following, that we have say starting x vector and a y vector, its covariance structure given by the blocks sigma 1 1, sigma 2 2, sigma 1 2 and sigma 2 2, and the correlation matrix derived from that covariance matrix. Now, we are trying to replace these by pairs of canonical variables u1 v1, u2 v2, up to the point where we can form the pairs, that is the last pair. If we assume that p is less than or equal to q, then the last pair will be u1 paired with up paired with vp. Now, the remaining vp's, that is vp plus 1 to up to vq, are not going to be paired, but what we are trying to say is that whether we can obtain a number k, say, which is less than p, and say that k of these canonical variable pairs are enough to capture the covariance structure or the correlation structure between x and y. That is what we are going to achieve. Now, how we are going to do that is through this particular technique. Now, when we had defined this canonical variables, we had seen that this u1, u2, up, we are not actually working with the standardized variables, and hence I am just writing this as Ax. To work with standardized variables are once again not difficult, it just follows from these calculations. So, that was given by this A times x, wherein we had obtained this A as E1 prime, E2 prime, EP prime, this times sigma 1 1 to the power minus half, and similarly we had the other component, this is, remember, p by 1 and this is q by 1. This we had denoted by a matrix B times y, the original random vector, which was q dimensional, and here this B matrix, as we had seen, was given by this f1 prime, f2 prime, fq prime times sigma 2 2 to the power minus half, right. So, once we have this u as Ax, v as By, where A and B are given by this. Now, note that what is the inverse of this A matrix? Now, the characteristics of this particular matrix, which has rows as E1 prime, E2 prime, EP prime, is that it is an orthogonal matrix, because EI vectors are orthonormalized eigenvectors corresponding to the p largest eigenvalues, and hence if we look at the inverse of this matrix, of course, its inverse exists, and that inverse is going to be given by sigma 1 1 to the power plus half, and the inverse of this matrix, which will just be the transpose of this particular matrix, because it is an orthogonal matrix. So, this is going to be given by E1, E2 up to EP, where these are the columns of the inverse of this matrix, and similarly this B matrix also is non-singular, with the inverse of B matrix given by the form which is sigma 2 2 to the power plus half that multiplied by the inverse, which is the transpose of this matrix, and which is equal to F1, F2 up to Fq, right. So, this is A inverse and this is B inverse. Why we are looking at this? Because we want to write this x vector, the set of original random variables, the vector of original random variables. Now, this x, if A inverse exists, is just equal to A inverse times u, and similarly this y vector is nothing but B inverse times this v vector, right. So, this is the x original vector p dimensional, and this is y, the original q dimensional, in terms of the canonical variables. Now, these two expressions here of x and y are going to lead us to this important observation. Now, if we write A inverse and B inverse in the following form, then we get something very nice, that suppose this A inverse is this matrix, we write that in terms of the columns of the inverse matrix as A1, A2, this is P by P. So, the pth column, let us write that as AP. Now, what is here AI? AI is the ith column, and what would that be given by? That is given by this particular term sigma 1 1 to the power half, that multiplied by the EI vector here. So, AI is sigma 1 1 to the power half times the EI vector. This is the EI vector, right. Now, similarly, this B inverse we write as B1 vector, the first column vector of the inverse matrix, and this last one is going to be that BQ, which is the qth column of the B inverse matrix, wherein similar to the AI vector, the BI vector, now this I is from I equal to 1 to up to P, and this BI is going to be given by sigma 2 2 to the power half times this FI vector for every I equal to 1 to up to Q, right. So, we have this as AI and this as BI. Now, realize that we are writing x as A inverse u here, so that once we are writing A inverse as this A1, A2 and AP vector, that multiplied by this u vector is just going to give us summation I equal to 1 to up to P AI vector, that multiplied by the ith component here of u. So, we have this as AI times ui, and y is B inverse times v vector. So, that similar to this x term here, what we can write is I equal to 1 to up to q now BI vector, that multiplied by Vi. Now, these two are important forms. Let me write as star 1 and star 2. Now, if we look at this representation of x, what is the covariance matrix of x? This covariance matrix of x is given by this covariance matrix. Now, x we are writing as I equal to 1 to P of AI vector, that multiplied by ui, right. Now, if we are writing it in this particular form, then covariance we are going to have this as summation I equal to 1 to up to P AI into this covariance between ui and the other term, which is of course going to be equal to 1, because it is covariance between ui and ui in this summation here, and ui and uj, that is going to be equal to 0. So, what we are going to get as covariance of x here through this calculation is that AI transpose, right. Now, if this covariance of x is given by summation I equal to 1 to P AI transpose, let us under this condition consider, let us consider the first k canonical variables only. So, we are going to neglect from k plus 1 to up to q terms and consider only the first k canonical variables. So, if we consider the first k canonical variables, then we are neglecting row k star squares from starting from k plus 1 to the n term, and then this x star vector is defined through that definition as I equal to 1 to k up to the terms we are retaining, because if you look at this x here, we are saying that we are chopping off at the point k here. So, we are not looking at this a k plus 1 to up to a p vector and only retaining a 1 a 2 up to a k, and under such a situation this x star is an approximation to x, and we are going to have that denoted by this summation I equal to 1 to k a I times u I. And similar to this, since we are only considering first k canonical variables, what we are going to have as y star is the following, that this also is I equal to 1 to k b I times this v I. So, this basically is what we are having as x star and y star as when we are looking at the first k canonical variables. Now, realize that if we look at the covariance matrix between these two components here, well, that can be computed. Let me first look at a simple term here in this lecture. So, the last thing in this lecture what we are going to see is that this what is covariance between x star, what is the covariance of this x star vector, that by the similar logic is going to be equal to I equal to 1 to up to k a I transpose. So, this covariance matrix of x, which is summation I equal to 1 to p, is now being approximated by the covariance matrix of x star, which is the same summation up to the term this k. So, we basically are trying to say that the terms from k plus 1 to up to p in this sum here are neglected when we are looking at this. Similarly, this covariance matrix of the y star vector is going to be given by summation I equal to 1 to up to k b I into b I transpose. So, we will end the lecture, this lecture here. We will continue from this particular point in the next lecture.